My name is Bill Green. I'm the director of the MIT Energy Initiative. I want to thank you all for coming out on this gray day to hear our next speaker in our seminar series, and welcome to our fall colloquium. This fall colloquium launches the second year that the MIT Energy Initiative is sponsoring a speaker series with the intention of bringing energy leaders to campus to discuss issues that arise in the energy transition and new technologies, also policy and business issues related to that. Part of the MIT Energy Initiative's role is to be a convener of leaders in industry, government, nonprofits, and academia to help them identify the innovations and ideas that have the potential to speed up the energy transition. And today we have one of those leaders, Kurt Kelty. Kurt is the Vice President for Battery, Propulsion, and Sustainability at General Motors. Earlier in his career, Kurt was the Senior Director for Battery Technology at Tesla. Between his time at Tesla and joining GM, he was the Vice President for Commercialization at Sila Nanotechnologies, which is a battery materials company. Kurt has his undergraduate degree from an excellent college, Swarthmore, which happens to also be my alma mater. And he completed his postgraduate business degree at Stanford. He spent more than 3 decades working on battery technology at energy, automotive, and battery companies. And we are very fortunate to have Kurt here today at MIT to share his experiences. Very welcome, Kurt Kelty.
Thank you. It's a pleasure to be here. Thank you for inviting me to come speak today. I had a wonderful afternoon with many of you. I went to some different labs and met with different professors, and I had the benefit of learning all day from you. So hopefully I can return the favor here. It's also great to see so many people interested in batteries. I've been in the battery industry for since the early 90s, and when I joined, it was nickel metal hydride was the chemistry of choice. But back then, I'd go to cocktail parties, and you say you're batteries, and people would go, boy, go talk to somebody else. But nowadays, you say you're batteries, and everybody has an interest. They have questions. They want to know, why doesn't their EV get better range and when it's cold? Or whatever. You get hit with all sorts of questions. So I'm not surprised seeing so many people here, but I love it. It's great to see. So I'm going to talk a little bit about what we're doing at GM, building really an electrification powerhouse, is what I'd like to refer to it as, and I'll talk through some of our products and what we're doing on the battery front. So first of all, let me talk about some of our products here. So we're building really industry-leading products in many areas. For example, our EV trucks are the fastest charging trucks in the market. Our trucks also are the longest driving range. So here's a Chevy Silverado. It's 490 miles of range, which is the longest of any EV truck on the market. And our engineers actually had some fun this summer. They decided to see how far you could actually drive it on one charge, and they put the right amount of pressure in the tires. They drove at a very slow pace on the back roads in Michigan, and they actually achieved over 1,000 miles of driving, which set a new record. We achieved these results with really it's a combination of different groups working really closely together in collaboration. Where you've got the battery team working closely with the motor team, working closely with the vehicle team, and all these teams working together trying to optimize around a system solution that works really well. And that's why we're able to achieve such a feat with the Silverado here. We've also got the most affordable EV that drives 314 miles on a single charge. This is the Equinox. It's the second best-selling EV in the market in the U.S. today. And we're also about to supplement our affordability range vehicles with the Bolt. We're going to reintroduce the Chevy Bolt in the next month or two. Before the end of the year, that'll be shipping. So so we're really looking forward to that on the affordability side. Now, when you go to the other end and you look at the luxury vehicles, the Cadillac Lyriq is actually the #1 selling luxury EV in the U.S. market and the Canadian market. And we actually got the award in Germany a couple months ago for the best luxury vehicle of the year in Germany, which is the first time an American brand has gotten that. This is a vehicle I drive. This is a great vehicle. The other thing is, so we're doing well in really some of the technical side in terms of driving range and charging, the affordable cars, the luxury cars. And what's happened is we now have tremendous market share. Now we're number 2 in the market, the EV market, commanding number 2. We're almost double our nearest competitor in the market. We've doubled our sales over the last year. The last quarter, which ended last week, at the end of September, actually was our best quarter ever. We've never shipped so many EVs before. So we're really, so these vehicles are actually, you can see the impact on the market where we're selling a lot of them. We'd like to be selling more, but we're selling a lot of them. So we're quite pleased with that. So my team is really working on 3 things here. And those 3 things are trying to drive down the cost of batteries. We need to get more EVs out there. The way you get more EVs out there, you've got to drive down the cost. How do you drive down the cost? Well, it's the batteries. The batteries make up about 30% of the cost of the vehicle. And so you've got to drive down the cost. So my team, I'm in charge of basically everything battery at GM. And so my responsibility is 3 things. We got to drive down the cost of our batteries. We got to continue to improve the performance of the batteries. And when I say performance, it's charging speed and it's energy density. Those are the 2 things we're focused on while keeping safety in mind on everything we do. And then the third thing is it's all about localization of the supply chain. We've got to build up our resilience and our independence here in North America, so we're not relying on materials coming from China. So you can what we can see here is these are pictures of our R&D facility, Kettering. And I should take this moment to introduce George. Where are you, George? So George heads up our battery R&D, and he's based in Kettering, the lab that does our early stage R&D work. What they do there is they're looking at new materials, new processes, and they're building coin cells. They're building multi-layer pouch cells in this facility. This is where Kettering, the R&D lab here, is the first auto R&D center ever established, and so it's got a rich history. And more relevant to the EV industry, this is where the EV1 was initially developed. It was the first mass production EV, and also where the Volt came out of. The Volt with the B being the first mass-produced plug-in hybrid. So it's got a rich history. And then here on the street, we've got the Wallace Center. And the Wallace Center takes the output of George's team in R&D, and they take it the next level. So they're taking the coin cell, the multi-layer pouch cells, and what they're doing is they're building full auto-scale cells, like 200 amp hour pouch prismatic cells. So these are cells that you can actually, because not everything, just because it performs well in a coin cell or a multi-layer pouch cell, that doesn't necessarily mean it's going to perform well in a large scale cell. And so we've got to go to that next step of building the auto scale cell and then testing that out and seeing how that performs. So it was really important for us to get this online. It came online about a year ago, a year and a half ago, where we started to be able to make cells and really test them and understand how the performance really does change in a vehicle. And then right down the street, no, it's not down the street, it's actually on the other side of the street, is the Battery Cell Development Center, which is under construction now. It's going to be done by the end of next year. And what we're doing here is we're going to be building much larger scale, so up to a 0.5 gigawatt hour of production. Still not mass production, but it's taking that. So you can see we've got multiple stages. You got the R&D stage, you got the development center stage with Wallace, and then we've got BCDC here, and the next step would be mass production. Now we're also doing mass production with our partner LG Energy Solution. So we've got facilities. It's called Colloquium. It's our factory. It's a 50-50 joint venture with them. And so we build our cells all there. And we're actually the largest producer of battery cells among any of the automakers in the U.S. So we've got 2 plants that have 40 gigawatt hours of capacity at each one. And we're our OEE, our operating efficiency, and our yield will match any of the best Asian auto manufacturers. We really have gotten good at manufacturing cells. And this is kind of the missing link here, is that pilot scale of production. So that'll be ready next year. But you can see the resources that we're putting into battery development, because it's just so critical for the future with the EV industry growing like we expect it to. Now, this is showing some of the capabilities we've developed in the virtualization space. What's really, all of you that know that are in the battery space know how long it takes to do R&D, where you develop a cell, you put it under test, and then 6 months later you find out, oh, it worked well or it didn't work well. Let's tweak this little parameter here and make them again, and then you have to wait 6 months for the results. So what we're doing is we're putting a lot of effort into the virtualization space. So if you want to modify, you want to change the nickel content ever so slightly, we can very quickly model, okay, how's that going to affect the energy density, the safety, how's that going to affect the charge capability? And we can look at that at the cell level, and the pack level, and the vehicle level. How's it going to affect our crash testing? And so we can do all this modeling right up front. It'll take a couple of days, where it used to take months for us to do this. So this is something we at GM we're putting a lot of effort into to really getting the virtualization such that we can eliminate doing a lot of the physical testing. You can see the product lineup we have here. There's a couple more vehicles that aren't shown here, but we've got 12 EVs now on the market, and with the addition of the Bolt, it's going to get up to 13. So we've got more EVs on the road than any other automaker here in the U.S. Boy, it just wants to go to that next slide. Now, so what we've been doing is each one of these vehicles is using the same cell. It's a cell that's made at Colloquium. It really wants to go there. I'm going to set this down. So we make the cells at Colloquium. Yeah. Well, hold that thought. So we make one cell right now, one module, and it fits into all of our vehicles. All 12 of our vehicles use the same module, and we have a different number of modules in several of the vehicles. That's how we're able to customize it. But going forward, our volumes are going to be larger quite a bit, and so we can actually come up with a custom form factor, a custom chemistry going forward that we didn't have the luxury of being able to do before because our volumes were too low. And what this slide was really pushing me to talk about was the form factor. So we're going forward with a prismatic cell form factor instead of pouch. Until now, it's been pouch. In the future, we're going to use a prismatic form factor. And what this enables us to do is we're able to cut down a lot of the parts. Almost 50% of the parts now are going to be eliminated in our next generation battery compared to the ones that we're producing today, just by going to this large format prismatic cell. And then the other lever we have is on the cell chemistry side. And I'm going to talk a little bit about the different chemistries that we're using going forward. So in order to talk about that, let's first talk about where we've been in the past in terms of the history. So traditionally, the NMC chemistry came out about 2 decades ago. And that was a real first, really high volume production cathode material. And we called it NMC 111, and we called it that because it was equal parts cobalt, nickel, and manganese. That's what the cathode was made of. And then what happened was there was a huge amount of effort in the industry to focus on 2 things, and that was improving performance and reducing the cost. And the way we did that, the whole industry was working on this, GM was working on this, and the way we did that was we reduced the cobalt, which is the most expensive element that's in here. And each one of these elements has their specific role here. The nickel, the big advantage there is it provides the high energy density, whereas the manganese really provides more of this structural integrity. So they've each got a different function here, and the cobalt is more on thermal stability. They've each got a function, but we were able to, as an industry, reduce the cobalt and add the nickel. And that led to a significant cost reduction by having it be majority nickel. So we call that a high nickel cell. So in the last 10 years, that's what the majority of cells that were produced around the world. Well, outside of China. China is really an LFP based country, which I'll talk about shortly. But and all of our GM vehicles use this high nickel, or maybe it's called NMC 811. There's different names for it, but it's got a lot of nickel. So what we did at GM is we've been working on this for many years of how do we make it even more affordable? How do we drive the cost out further while still maintaining the range? And that's when we developed what we call LMR. We announced this in March. It's a big deal for the industry by shifting the chemistry from the high nickel to an LMR. And what we did was we took the next expensive thing, nickel, and reduced that way down and added more manganese. Just for reference, the price difference here, the nickel is roughly $15 a kilogram, something like that. Manganese is about $2. It's a huge difference. Manganese is abundant around the world, and it's very economical. So there was nothing new in terms of LMR. People knew about it, but they didn't know how to commercialize it. They didn't know how to make it work in an EV. As it's been around 25 years ago or so, it was invented here in North America. Two different, Argonne and Dalhousie University, kind of invented it at a similar time. But in different research groups have tried to develop this, but they've been unsuccessful. And we now have finally figured out how to commercialize it. So we're actually going to be the first to market with this in 2028. We'll introduce it in our trucks. So it's something we're quite excited about. In fact, yesterday we won an award at the battery show for the Innovation of the Year in the battery industry. So we're quite pleased with that. And you can see here what the advantage that it has. LMR has a cost that's similar to LFP. Now, LFP is the chemistry of choice in China. That's generally their chemistry. It's known for low cost, high cycle life, high safety. So that's kind of what LFP is known for. And then in the NMC over here, the high nickel, this is what is in most cars on the road here in the U.S. And what it's known for is a high range, but it comes with a high cost. And so what we try to do with LMR, you can see here, is get something that has a comparable cost to the LFP, but a range that's closer to the high nickel. And that's what's really a breakthrough. We're looking at this as a potential way to leapfrog what they've been doing in China. Now, the other thing that we implemented by using LMR is we went to a much larger prismatic form factor. And what we can do with this is with our form factor, we can get 33% more energy than an LFP cell. With all things being equal, 33% more energy at a comparable cost. And that's really what is great. So you can get the range at a reasonable cost. And if you then put this into a vehicle, so here we've got a Chevy Silverado. This is driving 490 miles on one charge. If you put LFP in there, you can still get 350 miles, which for most people is excellent. That's great. And the advantage is you can save over $6,000 on the battery pack cost. So it's a real cost savings. Now, what you can also do is you can put LMR in there, and you can get over 400 miles of range at a cost similar to the LFP. So that's why the LMR is such a big deal. Now, the other thing is that the supply chain is basically the same as the NMC supply chain, which is in the Western world. It's in Korea and it's in North America. Those are our sources. Whereas LFP, the supply chain is all based in China. So it solves the three things that I mentioned earlier that our group is working on. It's cost that we're working on, it's performance, and it's localizing the supply chain. And LMR checks all three of these boxes. Now, we're also working on some other areas besides EVs. We're figuring other markets for batteries. And many of you here are probably working on some of this also, using it in storage applications. So we are working with Redwood Materials based in Nevada. And what we're doing with them is they're taking our second use batteries. So batteries that have gone through their initial life in the vehicle, they're done in the vehicle. Done in the vehicle means they've got like 70% of their original capacity, but owners don't necessarily value the car that much when there's only 70% of the capacity. But the battery's still good. So we can take the battery out and we can use it in a second application. So that's what we're doing with Redwood. Did it moved again? And you can kind of see here in the background, but these are battery packs that are situated on the ground on cinder block, and they what they're doing at Redwood is it's a plug and play. You just bring in a battery pack and plug it in, and they're agnostic in terms of which battery pack it is. It's pretty neat technology they've got. So we're working with them on supplying them with batteries that are from the market. And right now we've got I think it's like 68 megawatt hour system that's up and running right now. It's powering an AI data center by Crusoe in Sparks, Nevada. So it's the largest second use battery pack microgrid in the world. So this is the first one we've done with them. We'll be doing more. But there's other uses for batteries as well. And one of those is vehicle to grid. And this is something I'm really excited about in the future. Our vehicles will be capable. They're capable today, but you have to put some add-ins in your garage. But in the future, it'll be much more seamless for customers to connect up in their home, and they can, however they set it up and however the relationship is with the local utility, they can end up charging their vehicles at night when the electricity prices are really low, and they can discharge it during the day when electricity rates are really high. And initially we can do this with our existing batteries without any improved cycle life, because if you look at this, like when we talk to PG&E in California, they only need this for about 20 days a year. It's not something you need to do every day. About 20 days a year is when they've got so much demand on the grid that they need to draw from these sources. And where they're drawing from right now are these peaker plants, which are incredibly polluting. Unfortunately, often they're diesel powered or they're older plants. And so instead, what they can do is draw upon vehicles. And that's the direction we're going with our batteries and with our customers, to enable them to use our battery packs in the vehicle, in these vehicle to grid applications. If we're talking about the EV market, we can't ignore the infrastructure, the DC fast charging. This is one of the biggest challenges that the industry faces. I was just traveling this weekend up in northern Michigan, and in an area I'm not familiar with, so I went to new charging stations. I did charge 6 times over the 3 days, and only one of them worked seamlessly. It's still the grid is still not good enough. Now I was able to charge and it all worked out, but it shouldn't be that way. It should be seamless. You drive up to the station, you plug in. You shouldn't even have to use an app. It should just automatically work. And so we've still got some work to do there. I'll tell you, it is so much better than it was even a year ago, 2 years ago. I've only had an EV now for 12 or 13 years, and each year it gets better and better and better. So there's no question it's getting better, and we're gonna get to a point where it is seamless, like going into a gas station. But right now we're still in that transition phase of building it up. We've got now roughly there's about 250,000 charging posts around in North America right now, and then by 2030 we'll have about 35,000 stalls of fast chargers across North America. So we're deploying more, and Jim's heavily involved in this. We're investing in companies that are doing this and partnering with them. Our partners are Flying J here. You can see the GM Energy logo on that one. EVgo, ChargePoint, and then another one is Iona. Iona is the joint venture with several other automakers. And all of these were working on deploying fast chargers as fast as possible, and also trying to work on the uptime, because that's also an issue with them. Okay, and then the other thing I want to briefly mention is the supply chain. And the supply chain is something where we've we're really focusing on localizing this as much as possible. We're starting with the cathode materials. We've had investments with POSCO, with LG Chem. We're investing in bringing that, and the cathode is the most expensive part of the batteries. So we're doing that with on the cathode. We're doing other active materials as well. The separator electrolyte, we're going to localize that by the end of the decade. We're working to bring all the critical elements, whether it's the nickel or the graphite, each one of these closer to home, such that by 2028, our local content will increase eightfold compared to today on our battery cell manufacturing. This is extremely important for us to get this localization done as quickly as possible. And then finally, just to share a little bit about the future of battery manufacturing in the States. I've been in this business for over 30 years, and when I first joined, well, let me tell you, when I first joined, the battery industry was exiting the U.S. There was Energizer and Duracell, and that wasn't it. And they were getting crushed with lithium ion. And I went to Japan. That's where everything was happening. Japan back then was China of today, where the world was centered around Japan. They were going to conquer the world with their manufacturing ability. And so I went there and I helped the Japanese manufacturing with battery cells. And what's been interesting is over the last 5 or 6 years, it is totally reversing, where we're really developing a lot here in the U.S. We've got, since 2019, we've got $125 billion that has been invested or announced investments in either EV manufacturing or in battery manufacturing. And this spans, it's over 18 states. We've got about 113,000 employees that we've added to the payrolls. So it's been amazing to see what's been occurring in bringing those jobs back here and bringing that manufacturing back. So, I'm really optimistic about the future in terms of battery manufacturing in EVs here in the U.S. We've got the technology here to make it happen. We've always had the innovation here, and now we're getting more and more of the manufacturing. So we're getting that all together. So we've got just tremendous opportunity here that I'm hopeful that we're going to be able to take advantage of and really build a massive battery industry here.